Before we start, just one small request. Some of the showing rings are very fine, so please come down if you want to see everything. These two upper parts, please come down. There are enough places.
Okay, so let's go ahead.
Okay, let us start. Dear ladies and gentlemen, dear guests, we will have now the unique opportunity to hear the story about the roots of the J integral and some of its applications and extensions. This lecture will be delivered by Professor James Rice himself. And I needed to emphasize that because J integral is parameter that we know as the basic, most important fraction mechanics parameter as introduced by Jim in 1968. So coincidentally, this is the 50th anniversary, and all pieces of puzzle just naturally were put together that we have such an event in the scope of our summer school and in the scope of European Conference on Fraction 22. Now, to introduce Professor James Rice is practically impossible. Therefore, I have prepared, and you can find these 2 pages on your tables. On the front page is the history of fraction mechanics presented as Professor Rice's references. If you follow his references, you follow history of fraction mechanics. On the back page are extracts from Professor Rice's biography, and now, ladies and gentlemen, Professor James Rice. Jim, please.
Well, thank you very much, Professor. And thank you all for being here. It's a bit of a walk through history for me. It is the 50th anniversary of the publication of my paper on the path-independent integral. But also, it turns out, and this was learned at least by me only after this adventure with the J integral was begun, but a lady named Emmy Noether wrote a very fundamental paper which as I'll explain as we go along, is closely related to the J integral. She wrote that in 1918, so this is also the 100th anniversary of a very influential and related paper. So good timing.
Yes.
Okay, so there we have things up there. And you can't read this, and it's not necessarily intended that you could. You will be able to read things that come later. But this was just the main paper for my PhD thesis, and I put it up here just to emphasize that it actually had absolutely nothing to do with the J integral. vaguely related to fracture mechanics because I was a graduate student at Lehigh University at the time in the US, and among the faculty there was a then young person named Paul Paris, and Paul had been at Boeing Aircraft Company before and had brought to Lehigh when he moved there a lot of interest in problems of fracture, and of course Boeing's airplanes fly through sometimes turbulent air, so there was a lot of interest at the time in how turbulent fluctuations, that essentially random variations in stresses in aircraft structures would affect fatigue. So that was the connection to fracture mechanics in my thesis. Yes, and I did actually start while at Lehigh, in fact, even as an undergraduate there, with a faculty member named George C., on this problem of plane problems of cracks in dissimilar materials, cracks along the interface between materials of two different properties. And we just heard, most of us this morning, a marvelous summary by Leslie Bonk-Sills of her work in just greatly advancing this field beyond the feeble start that we made of it. But there was no relation to, well, this was, I guess, my first venture in fracture-related things. Now, this was an important step because once I got interested in fracture, I became absolutely fixated on trying to understand what this Griffith energy balance was all about, and if and how it could be extended to other than linear elastic materials, especially to elastic plastic materials. And this was the first of a couple papers I wrote around that time. It was presented at the first International Congress on Fracture. And it was an examination of the fracture mechanics energy balance from the point of view of continuum mechanics, but essentially it tried to find ways of taking integrals in the field near a crack tip in order to get something which could be equated to a dissipation during fracture. I can't say this work had any great successes, but it's how I got fixated on this problem. Around the same time, I started to solve everything that I could in the way of elastic plastic analyses of crack problems. And these are very hard for the problems of most general interest, which would be cracks which you pull in tension and open, what we call now mode 1 cracks. But it was a lot easier if you would look at anti-plane strain cracks. So here's a crack. Sorry. Yeah, here's a crack, and this is in a body that is loaded, so that the territory up here on top of the crack is deformed and coming out of the board towards you. The territory on the bottom is going into the board away from you, and that is called anti-plane strain. And in fact, in that case, and independently, Neuber in Germany did such work too. It was possible to get a fairly complete description of stress and strain near a crack tip for arbitrary nonlinear relations between stress and strain. So that got us started into the details of analysis. Of course, that's a very artificial case compared to the needs of most applications. It is anti-plane strain. The particles are displacing in and out of the plane of the figure, whereas we're really interested in problems where the crack is being opened by loadings. And this is the, I wrote a summary paper on what I had learned from these various studies in 1967, and as part of that, I had this paper. It's also a paper that appeared in that same year in a paper by Gennady Chertonov, working in Russia, and submitted, published in 1967. I must say, we always thought in the West that the Russian system might be on the verge of collapse because of inefficiencies, but that certainly was not true about Russian scientific publishing. As I'll explain later, Gennady wrote his paper on this in January and it was published in April. I wrote mine and it was published 10 months later. So, so the Russians were at least very efficient in scientific publishing in that era. Okay, but as part of that work, we both had discovered the possible relevance, and a fellow at MIT, Frank McClintock, also had discussions which were very helpful for my understanding of this, but how a classical field that many of you who studied plasticity theory and plane strain flow will recognize as a slip line field, and how that seems an appropriate description of the near crack tip state under plane strain conditions. And it's sensible to assume plane strain because as you load the cracked body, the material that's plastically deformed wants to suck in laterally, but it's not going to be allowed to do that because of constraint of the material that lies further away from the crack tip. So effectively, you get a situation where
keep it away from.
okay, sorry.
Just keep it away from.
Oh, okay. We get a situation where you effectively get plane strain field. And the field itself is a famous one from Ludwig Prandtl's work quite early in the previous century, where he had encountered this field and the problem of having a half space on which you had a punch that was being pushed in, a line punch coming out towards you, and this was a field that appeared in analysis. Oh, I'm doing it again.
Keep it close to your mouth and away from you. Is it possible? Okay? No, no.
I'm not going to talk into this. We'll just let it lay.
Then talk to this.
Okay. Oh, I see. I have to talk to one of these. Okay. Okay.
Or
Yeah. Then I'll talk.
just a moment, sir.
And do I push
It's better
anything?
because there is no antenna.
Hello? Everyone hear me?
Yes.
This is being amplified? Yeah, good. Okay. Thank you. Well, this is my paper in any event on the path-independent integral. As I just complained, it had a fair wait until it was finally published. You might think there were lots of terrible reviews of the paper. No, there wasn't. To my great frustration, after waiting all that time, only one review came back, and that review said, Rice has already talked about this stuff at a conference, so there's no real need to publish the paper. Happily, the editor didn't accept that proposal. But to look at this in more detail, what this all involves is thinking of a deformation field, which is essentially 2D near a crack tip, and looking at a certain integral around the crack tip on paths that start on the bottom surface of the crack and work their way around to the top surface, as you see in these paths here. And you can equally do it not for a crack, but for a notch which has flat surfaces except in a region near the tip, and the same formulation applies, but this integral is independent of path. You can take any path you like from the bottom flat surface to the top, and you get the same value, so it's path independent. And then an immediate application of this was to working out the form of singularities at crack tips in nonlinear materials. So the easiest one to deal with is one where at large strain in the plastic range that stress went as strain to some power, so-called power law hardening. And this is work I did with Joran Rosengren, who unfortunately passed away early, but he was a PhD student from Sweden who was working with me in that era. And as it happens, virtually identical work was being done by John Hutchinson at Harvard, a longtime friend of mine. I was at Brown at the time, Brown University. But John had approached this in a very different way. He didn't know about the J integral. I later showed that work to him, but he was simply saying, well, I've got a crack and I'm going to look for solutions where stresses goes distance from the crack to some power times some angular dependence. And so we ended up both at the same place in getting these so-called HRR fields, and their property is that the product of stress and strain is an angularly dependent term divided by distance from the crack tip, at least asymptotically as the distance from the crack tip goes to zero. So these were the HRR fields, and their existence and properties just followed at once from the J integral, though as I said, John got there from a separate route. Now, later on, after Noether's theorem had been discovered, Noether's theorem, as I said, was what Emmy Noether wrote is a paper which basically said if you have a conservation law in physics, that implies a integral that's independent of path. A very fundamental result, absolutely unknown in the mechanics community, but apparently it was widely picked up within quantum physics. And if you look at references to Emmy Noether's work, you will find hordes of references in quantum field theory to her work. But in any event, we didn't know about it at the time, and we're duplicating some of this stuff. And Jim Knowles and Eli Sternberg, neither with us anymore, but both at Caltech at the time, used the Noether procedure to devise these conserved integrals like J. J could be gotten by that procedure, but also other integrals associated with invariance under rotation and under self-similar scaling, and they've come to be called the L and M integrals. So they're all path-independent integrals. There's a family of them, J, L, and M, and the J is a vectorial integral. There are two components of that. And in fact, it's not that the mechanics community was utterly ignorant of Noether's work. There was, in fact, a paper written by a German mathematician, Wilhelm Dunker, in 1962, utterly unknown in the mechanics community until Knowles and Sternberg dragged that out. Someone had said, hey, I think there's a paper by a fellow named Gunther in Germany that you ought to be aware of. And indeed, Gunther is the first person to formally suggest applying the Noether's procedure to elasticity, and that was in this 1962 paper. Now, compared to things that most of us focused on fracture and dislocations and things like that find interesting, this was a rather dull paper because he applied his results to beams and plates and bending, which are not sort of forefront problems, or didn't seem to be. Of course, what's forefront depends on what I'm working on versus what you're working on in many cases. But in any event, it had no traction until Knowles and Sternberg rediscovered this paper more than a decade later. And it's now recognized to be a very fundamental thing on the way towards understanding these path-independent integrals. And as I said, Gennady Cherepanov published an expression for energy flux to the crack for an elastic, nonlinear elastic material, and that corresponds exactly to J. And also, one of the things I came to learn about rather abruptly, I was very happy with all of this work on the path-independent integral, and early in 1967, there was an international conference on fracture convened in Linköping, Sweden. A small conference, something like 25 attendees. It was all by invitation, so I was very proud to have gotten an invitation, but I had published a small slew of papers by then. And I went, making that the first presentation I would make of this J-integral idea. So I went there and I was happily presenting when a young man named Colin Atkinson from Imperial College jumped up and said, "That's Eshelby's energy momentum tensor." And indeed, he was right. it was, and Eshelby followed Noether and used her procedures to work out invariants. So we came to get the M integral too, so now we have J, L, and M, and I think that completes the part of the alphabet that can be made use of for this purpose. But they are the path-independent integrals, and as I've said already, paralleling my work, but having much better success in getting it published quickly, were Gennadi's things in Germany, where he basically discovered all the things I discovered too, and published them. Okay, I think that's that. Now, here's an application of this path-independent integral idea to processes of gradual decohesion. And these have been used in the literature on fracture in two different contexts, at least that I can think of. One was by Dugdale in Britain as a simple model for yielding of thin sheets in plane stress. He observed in the lab that when you had a crack in a sheet and you loaded it and it's plane, that you would often find that the plastic zone of necking developed in front of the crack. The material would suck in, and you would then have plasticity confined to a narrow line ahead of the crack. But equally, you can take the same model and reinterpret it at a vastly smaller size scale, at a near atomic scale, as a kind of description of fracture as you slowly pull atomic bombs out of range of one another, representing that in terms of a relation between a force per unit area and amount of separation. And it was then possible to show that J corresponded to the area under the stress versus separation distance curve up to the amount of separation that prevails at the crack tip. So it was another application of the J integral, which proved useful in some later applications. We also applied some of these ideas to very large plastic strains, at least compared to distances to nearby places where voids open up. And I think I'll just give that a pass. Now, a very important contribution was made by Matt Bakley and John Landez in 1971, and independently in that same year, Bertrand Broberg, working in Sweden, came up with a similar concept. And later there was a paper by Bucci, Paris, and Landez called J-integral estimation procedures, which involved ways of estimating J by taking its definition of the rate at which the total work of deformation of a specimen changes when you change the crack length, and using that to devise an experimental way of actually estimating J. And this was of great interest because at that time in the US, we still believed in building nuclear reactors, and there was great concern over their safety and the ability of them to sustain cracks when highly pressurized. So that had, it caught rightly quite a bit of attention. And A summary of some of that is in this paper. Well, I'm on that paper, but it was their idea to do this. I forget. Oh, and I think this was about simpler ways of estimating what might be learned from such experiments. Okay, and then a later paper showed how you could, if you had a very deeply cracked specimen, where the crack runs almost up to the end, and if it's loaded and bending like this, you can see how you can evaluate J from experimental measurements of the opening torque versus the amount of rotation of the ends. So those were kinds of applications. I think I skipped over something, and I don't notice it on my slides, but somewhere in here I should have mentioned, and I don't know what happened to that slide, but also a very important step that Landez and Bakley participated in, and there were others who had the idea independently around the same time, was applying the J integral idea to creep, high temperature creep. And that had quite a successful history too. Been through that. Yeah, so now here's an application that goes a bit outside of conventional materials engineering, but it was an application that was made by Andrew Palmer, who was then at Cambridge University in England, and myself. Andrew had gotten his PhD at Brown with Dan Drucker and visited often, and he and I collaborated when he visited, and later when I went there for a sabbatical to Cambridge, UK. But we got interested in how slip surfaces develop in clay slopes, especially heavily over-consolidated clay. That means it's stuff that has been smashed down and lost a lot of its water content, but when it deforms, tends then to dilate during shear and suck in any water that's available nearby in the sediments. And this was the application that we made there. So this shows the path of a path-independent integral around such a mode 2 shearing crack. And the evaluation of J from things that you could measure from a direct shear apparatus for homogeneous deformation before the onset of localization. And that gave us this formula here, where the tau sub r is a residual resistance on the sliding surface. Now this got picked up in a much bigger community, namely the earthquake dynamics community, because a fellow named Ida proposed this idea of slip weakening, which had begun to become rather popular in engineering fracture mechanics, that you could think of a relation between stress and amount of relative shearing displacement, and applied it to earthquakes. And he had caught in pre-publication form a copy of our paper and used that to develop what is now called the slip weakening model in earthquake science. We also tried to make some such applications at a near atomic scale. So this at first has nothing to do with the J integral, but I'll get to it later. A fellow named Rob Thompson and I began to look at the question of what is it that makes a material brittle versus ductile, a crystalline material in particular. And the hypothesis we examined is that if you could load a material so that you manage to nucleate a dislocation from the crack and blunt out the crack before you made it break in tension, then the material would not be crack sensitive and it would be ductile. It would be a metal like copper versus something else that's quite brittle. So in using that, again, the J integral came into that. I tried to take that a little further, and I was happy with this work when it was done, but since it was done, Bill Curtin and his co-workers in Switzerland did direct atomic modeling. We tried to take an atomic scale phenomena and treat it by continuum theory, which means you're walking on shaky, rather tentative ground, and Bill Curtin showed that in some cases it was very shaky ground, nevertheless. But our simple continuum approach could look at a relation for shear stress versus separation distance and use that to estimate when the shearing near a crack tip would reach a point of instability so that you spit the dislocation out. So it would be the onset of the plastic yielding near a crack tip. And an important parameter that comes in is this so-called unstable stacking fault energy. If you think of taking two atomic planes and sliding one by the other, then you're going to have a big increase in stress, but then beyond the maximum stress, you're going to come down again because you will have succeeded in sliding one atomic spacing. And the energy put in per unit volume to do that straining is called the unstable stacking fault energy, gamma US. I'm sure you can't read the US as subscripts, but that's for unstable stacking. And this led to a number of investigations of atomic scale phenomena controlling brittle versus ductile response at crack tips. Oh, here's a picture of that schematically of what's involved in that unstable stacking energy. You imagine you're shearing these blocks of atoms, and as you shear, ultimately you're going to come to a peak load, and then it's going to be unstably downhill from there. But this area under the stress versus amount of slip curve defines that so-called unstable stacking energy. So that was, again, another application of J. Now here's one that was totally off the wall and unexpected to me, but at one point I spent a sabbatical in France, and I met a very bright and productive colleague there, Martine Benamar, and she was generally interested in, well, she was generally interested in everything, but that included fluid flows and the phenomena of electromigration. Now, electromigration is not quite a fluid flow, but it's the idea that if you have a complex alloy and you're sending an electric current through it, as the current moves, you put different atomic level forces on different atoms in the crystal, and that causes a drift of material. That's called electromigration. And it causes voids in conductors to move in time as current flows. And there was a long-standing problem in that field that numerical solutions gave a pretty clear answer to this problem of how wide would the gap be if you put a uniform electric field on and let the problem of electric charge flow, electroosmosis as it's called, go on, and how that would advance a cavity. The trouble is, no attempt up to this time succeeded in estimating the width of that cavity, and that turned out to be possible using the J integral with no further detailed calculations needed, just taking the contour around an outer boundary and along the border of the growing void itself. And this gave us that lambda would be 2/3 of the channel thickness. That agreed very well with numerical systems, simulations, but as Martine added to the paper, I couldn't add it because I wasn't that much into the area to be able to say this with any authority. But it is worthwhile recalling that all the standard methods of complex analysis, like the Hutograph methods with conformal mapping, Safman-Taylor, Taylor-Safman, Green-Safman, and Schwarz's method, complex function theory, failed to find this result, while they were very successful for other things. So this was some unique contribution that apparently no one had yet thought of any other way of finding, but it gave us the configuration of a void growing in a conductor by electromigration. Okay, back to large-scale things in the Earth. This is a picture of the Western Antarctic ice sheet. It's the biggest ice sheet on our planet. The next biggest is Greenland, and then we have regions of permanent ice cover like in the Arctic. And these are results from satellite measurements of velocities of flow on the surface of the ice sheet, horizontal flow as the ice moves out towards a sea here. Let's see if I can make this work. Yes, this is ocean, but it's ocean covered by a sheet of ice. So here the ice is bedded on what was old ocean floor. It sits on an old, essentially a clay-like mixture, water and soil that's compacted together. But here in this lower part, there's water below the ice. It's floating, so it's a floating ice shelf here, and it's a land-based glacier, though the land it's based on is normally below sea level here. So this is typical of the flow in Antarctica, and of course with interest in human effects on climate change, it's become of great interest to try to understand the mechanics and physics of what goes on in such processes. Oh, I'm sorry.
Okay, it's okay. Just hold it up.
Hold it up, okay. And speak softly. Okay. Well, it became of interest to us too to try to understand things. So for example, a particular margin that we focused on, and I don't want to divert too deeply into this, but it was this margin here where the borders of this reddish fast-moving stream moving more than 100 meters a year. Think about 100 meters a year. It means in 2 years, basically, the back of this hull has been moved to the front, or in 1 year, I suppose. Back is moved to the front. So even though on a daily time scale it doesn't seem like much, that's a lot of ice flowing out off of this Antarctic ice sheet. Well, fortunately, this is also a place that was very well instrumented with strain measurements, so it seemed an ideal place to do theory for because we knew very well the velocities on the surface of the ice, the strain rates near the edge. And in trying to analyze this problem, if you think about it, it really is a problem in anti-plane shear flow because the ice is flowing downward this way, down slope. Slopes are very small, of order 10 to the minus 3, so this is a greatly exaggerated slope in the figure. But the ice is slowly being pulled towards the sea with gravity, that's the loading. But on the side, there's frozen ice that's frozen to the bed, and so you have this channel, and at the edge you have something which could be interesting to try to analyze. So that is indeed what we did, and this was another application where the J integral came in handy. So here we're looking at a sheet of ice. This is the part that's locked because it's frozen to the bed, and this is half of the part. This is the center of the stream, but this is the part that's moving very rapidly downhill at these speeds approaching of order 100 meters a year. And this then resolves into an anti-plane strain creep problem, and there is a J integral for creep, and it's possible to use it as we did, and it gave us some simple solutions which we later found to be essentially correct by doing very detailed finite element simulations of the thing, but it gave us a solution for the strain field in the vicinity of this transition from slipping freely at the bed to locked at the bed, and the nature of the singularity in stress working rate. That's important because the rate of shear stress working on the ice equals the rate of melting, because the ice near these margins is temperate. That means it's right at its melting point. So at its melting point, ice doesn't snap its finger and turn to water and go away. You have to supply energy to it, the heat of melting, the latent heat, in order to convert it to liquid. And that is then the process, which means we have to do deformation work on the ice. So this gave us a very simple model, and it seems to be consistent, at least at a gross scale, with far more detailed numerical simulations we've done by conventional numerical methodology for this class of problems. These are a few more pictures about that. Okay, so might there be other applications lurking out there? And I guess this is my final slide. So it says, thanks for listening. Indeed, thank you. And thank you for inviting me. It's been a great pleasure to be here. It's also been a pleasure to see my former student here again, Ruzecca Nikolitz. And Professor Sedmak's family has been very prominent in mechanics and also in things relating to the path-independent integral. So it's been a very nice time to come. So thank you all.
Thank you, Jim. Thank you, Professor Rice. Please, any questions? Who has nerve to ask a question?
No nerve needed. There we go.
Hello.
That's a familiar looking face, yes.
I had a couple common stories that you might be interested to know. Back in the early days when Jim Bagley and I were using J integral as a fracture criterion, we always wrote in the paper, this is the J integral of Jim Rice. Well, one time I had an opportunity to go to a meeting in Moscow and met with Professor Cherepanov. And he said, you know, you keep writing, you're using J integral of Jim Rice. That's not correct. I thought of it first. So we actually looked at the literature, and like you said, he was 10 months before you.
Yeah.
But given his paper, it was not engineering friendly. Having that paper without yours, we would have never had the idea to try to apply it. And second story or comment, he talked about applying that to creep processes. And the beginning of that was where many of your ideas seem to come from. Sitting in the airport bar waiting for an airplane, we were talking, you were there with Jim Bagley and me and some other people, and you said, you know, if you take J integral and you take time derivatives of the displacements and strains, you get another time-dependent integral, which applies to time-dependent processes. So Jim and I said, oh, that sounds like a good idea, let's go try it, and it worked okay. So that's where that came from, sitting around an airport bar waiting for an airplane.
Okay. Sitting around in an airport bar can make you miss planes sometimes, too. Sorry, I have to turn this on. Yeah. Yeah, I'm not technologically swift. So sitting around in airplane bars can make you miss planes, but I remember meeting an old professor of physics from Ohio State University in an airport once, and he said, young man, as much as you travel, if you don't miss 1 or 2 air flights a year, you're wasting a lot of your time in airports. Okay.
Professor Rice?
Yes.
I have a question question regarding failure of single crystals where the dislocation interaction with the fracture is not dependent on the bulk, but it starts from the surface. And all your theories, you have always worked with plane strain case.
Yes.
So how can you map your results to the realistic single crystal where the fracture will start at the surface because of the dislocation starting from the surface rather than bulk? Any comments there?
Not offhand, not without seeing a diagram of is this on or off? Yeah, not without seeing some diagram, but you're saying that, I mean, I agree with you that typically dislocations start at a defect in geometry at a surface and then pile in that way. But you want to know whether the J-integral idea could be applied to that situation?
Yeah, maybe.
Yeah, well, to the extent that you're willing to treat the places where the dislocations have glided in as something that slips either freely or slips under constant shear stress, and then there's something blocking the array of dislocations at the tip, then you could take the point of view that you've got either a freely slipping crack or a crack that slips under essentially uniform shear stress. In both cases, the J-integral would apply to that. I don't know if anyone has applied it to that, but do it. Okay.
Any more questions? I will have one of my own. In the meantime, think about. So, there was a very important project from 1982 till 1990 between USA and ex-Yugoslavia on weldment fracture mechanics. We did a lot of work on direct measurement of J-integral. But just to mention, when John Landis was saying a couple of words, that actually, if I'm not wrong, he is the person first to measure J-integral.
That, probably so. Do you agree? Okay,
here
good.
it is. Good. Okay, then later on, according to a paper written by OHJI, what is the pronunciation? I don't know, OG or something like that. In STP 591, there was some original work on direct measurement of
Thank you.
J-integral.
Thank you. That's what I was trying to think of and did not think of. But they also, Oji and Shiro Kubo and others in Japan also had, I forget whether it was after John Landez and Bailey or a comparable time, but they also had this idea. They didn't get their act together and publish so quickly, but they also had been thinking about applying J-integral ideas to creep. John, do you know anything better on the dating of their time?
It was about 1970, I think, 76, something like that, and it was applied to rubber.
I think I actually had a note there on, is this still working? How do I go backwards here? Yeah, I think I actually had a,
We have time, so.
okay. So this. Oh yeah, here, and let's see if there's a note here. Yeah, I don't see that. Perhaps in what I wrote, there's a, I can't remember. But this, sorry. This reminds me, you have this handout, which is a set of papers and they can be downloaded. Don't tell anybody you're downloading them. I can't swear it's 100% okay with the publishers. Keep it quiet. But in any event, you will find among those papers, let me think if I can stop the one I'm after. Yes, okay, no, I'm not spotting it, but I'll mention another thing that is on here. I mentioned the significance of the work with Emmy Nerdish for all of this, and I think there's a download here. Yeah, I had trouble wrapping my head around Nerdish's stuff. As I say, it was heavily picked up by people in quantum field theory, but I had a lot of trouble, and I had to work on that, and I wrote a paper where I tried to teach myself what Nerdish was trying to say, and that's reference number 117 here. So if anyone wants a view of Emmy Noether's approach to conservation integrals, you could track her papers directly. You could also go and see what an amateur thought in describing what she did if you download 117.
And if I may add, whoever wants to hear more about Emmy Noether's theorem, tomorrow, 3:30, once again, if I'm not wrong, plenary lecture anyhow, plenary lecture in the afternoon will be presented by Professor Jovo Jaric, who happens to be here, although I cannot see him at the moment. Jovo, thank you. His title is a bit wrongly stated up to now, so this is a good opportunity to say that in the presentation tomorrow, as important part of it is actually Emmy Noether's theorem. So we will continue this discussion tomorrow afternoon, but let me go back to the question of direct measurement of J integral, because that was very well advanced technique of measuring it, and it didn't need any size, it didn't involve any size effect. It was just direct measurement of strains on one side, on the other side, on all the contour actually, and I always wondered why that technique was not more popular than it was. Can you comment on that? It was mostly done by Dave Reed at MBS and later NIST, and a lot of work we done here.
Well,
Let's just pull it up. I think it works. Yeah. Yes.
yeah, I'm probably guilty of not having studied the literature well enough. Around the time that John Mendez and Bailey were doing it, and then later as one of that Japanese group came to me as a visiting sabbatical visitor at Brown University, I got to know what his colleagues were doing, so that was my window on it, but I never, John Mendez could probably answer better than me. John,
Okay.
can you get that?
John, any comment on direct measurement of J integral?
Formulate the question again. Measurement.
Any comment on direct measurement of J integral? Done by Dave Reed and people from NIST.
Using a single load displacement curve to estimate J, which is...
I think he put strain gauges around a loop and measured a path integral.
Oh, that's a different technique, yeah.
Yeah, I think he did that, and that's, of course, the energy rate definition is what got Jim Bailey and me going for that, and it seemed like a direct way using energy rate, but he wanted to do the path integral, so he did measure that, and it seemed to work. Yeah. So, yeah. I knew David Reed very well, and we talked sometimes.
So we still don't know why it was not more popular, but it is one of the applications that was question mark at the end of the lecture. That's what inspired me to ask the question. So, please. Yes. Yeah, of course. Minecraft Puna.
The method of configurational forces or material forces has been quite popular, advocated by Morgan or Curtin in the US and Kienzler in Germany. They say it is a generalization of Eshelby and J integral, and it is applied to all and can solve most of all problems. How is your perspective or opinion on that?
I'm in favor of anything that works. Yeah, I mean, I had intended to, sorry. Yeah, I think those are clearly milestone contributions. They're rooted in Nerder's work. And I think if her, countryman, she actually moved to the U.S. and died in the U.S., but if Gunther had made more imaginative applications, things might have spread around faster. But not that many people were interested in bending beams and plates around that time. But that was already 1962, so it was a long time after someone could have done this. And I don't know how early the first paper by Jock Eshelby was. I should have tracked that down for this talk. 56. So Eshelby had already done it. And it was Eshelby who made, told at least me, and I think many other people, about the paper that I just mentioned by, who was it?
We'll check.
Senior moment.
You mean Gunther?
Good. There was Gunther.
No, Gunther. Yes, yeah, that's right. Thank you. Yeah, that's right.
Any more questions? I may add on my own that beyond the limits of original definition, J integral was applied in many situations by, in a way, modifying it, because it is a conservation law which can be generalized in the cases where limits do not allow its direct application. So there are a number of modified J integrals that cover, well, all possible, I think, situations and problems. So this question mark for the application, I think, is never-ending story. Okay, final offer for a question. If not, let me congratulate to Professor James Rice for this unique and fantastic presentation.
Thank you for this great opportunity.
Okay, now we can have welcome party, welcome cocktail, welcome reception, whatever, including registration desk, registration which will be on the second floor. But anyhow, we will be around and we can always find our way. Just ask any of us.